Okay, let's start. We are getting more and more students watching the tutorial, the lectures online. Thank you for the faithful one here. Otherwise, I have to lecture to a big empty lecture theater. For your information, we last week, I think Friday, we told you we have opened up 4 tutorial groups, and the sign-up rate is really low, and so the department has decided to close down the tutorial 12, 13, and 14, and so we'll only keep tutorial 11. Okay, I think basically no one would be affected. Okay, and coming back to the last lecture, one of the most important concepts in probability is the concept of independence. And people do make a lot of mistakes. Even, people in probability, researchers, they still make this kind of mistake once in a while. It is because the definition of independence is a mathematical definition. The definition is being about 2 events, and that probability of A intercept B is equal to probability of A. So this is a mathematical formula, and it's a very precise one. You really need both sides to be equal in order for the 2 events to be independent. So if they differ by a little bit, then it is still not independent. So that is where the thing is. By and large, we are using the English word independent because in some way it does capture the meaning of, whatever you know about one thing has no bearing on the others. So this intuition is still there, but sometimes at a certain point it may fail us. So a mathematical rigorous way of checking whether independence is this. Now this is this is a definition of independence. Another thing is about multiplication rule. So this depends on, this is not always true unless you know that they are independent, but this is true in terms of this is the multiplication rule. This is simply because of the way we define the conditional probability. So all right, and so now I think we wanted to do some related kind of thing. So I think we have covered this example, right? And so we must have covered this, okay, right? And so I think we have done this. This is a bit sort of weird. Because I think I have asked you to check when the sum is 2, you keep changing the problem. So one thing I don't change is the first die is 4, but I change my sum. So here I have 2 parts, that when the sum is 6 and when the sum is 7. In part A, it turns out when the sum is 6 and you know something about the first die, knowing the first die does influence, knowing the first die is equal to 4 does influence the probability of you are assessing the sum. Now, to give you a more extreme example, if you know that the first die is 4, and I ask for the sum equal to 3 or 2 or 4, immediately you know that this is impossible, right? You just can't have a sum less than or equal to the number you see in the first die. So meaning that once you, the assessment of the probability of the sum will be 0 if you know that the first die is equal to 4 when your sum is small. All right. So, but what is really surprising is something like this happen when the sum is exactly 7. Then the two events are independent. You can move on to look at the sum equal to 8 all the way up to 12. So you have altogether the sum equal to 2 to sum equal to 12. There are 11 such scenarios, and only one such scenario is the events are independent. The other 10 will be dependent. All right? So, okay, I think we mentioned this. And we look at the cards with replacement. These are crucial, and especially this is related to something like sampling or when people do survey. Now, when we are doing survey or picking sampling from a population, subjects from a population, we assume the population is fairly large. So that basically we assume the population is infinite, all right? So that when you pick one, you are not going to affect the proportion of the people that you are surveying. Only when you are in a situation that it is a finite population and the population is small, and the most reasonable thing is once you sample the person, you are not going to sample him again, right? But in order to make it into a certain scenario, we imagine that we put the person back into the bag, and then so he will still stand a chance to be picked. So this is called sampling with replacement, and this is the situation here. So the situation is I draw two cards from a regular deck, but I have to tell you later on whether the way I'm drawing the card, if I draw it one card at a time, whether before the action of the drawing of the second card, what am I going to do with the first card that I've drawn? So without replacements means you are not putting the card that you have drawn from your first draw back into the deck. But with replacement means that you put it back there and you redo it. So now the calculation is slightly different because the situation would be the same as before because you put back whatever card you have done. So you basically face the same fresh deck of cards before, all right? Now, of course, we assume that when we put the card back, we put the card back in an arbitrary manner so that you will not, every card will stand equally likely to be drawn again. Okay, so this is it. Okay, now we are trying to look at some of the situations. Let A be the event that an A is drawn, and C the event that a heart is drawn. So we wanted to calculate or to decide whether events A and C are independent. Now the independence is really checking three probabilities. The probability of A intersect C, so you have to calculate on the in one way, and then you have to calculate probability of A, you have to calculate probability of C. A common mistake I have pointed out in the last lecture is people compute the probability of A intersect C by multiplying the two individual probabilities. And then, of course, when you check them, it would agree. But this is a circular argument. So you have to calculate the probability of A intersect C from first principle, okay? Because if you are multiplying the two individual probabilities, you implicitly assume they are independent to start with. So, of course, you will verify that they are independent. So probability of A getting an ace, there are 4 aces out of 52 cards. So, and you draw the cards. Each card stands the same chance to be drawn. So you have 4 over 52. And then to get a heart, there are 13 hearts out of 52 cards. So 13 over 52. And what is A intersect C? A stands for ace, and C stands for heart. So A and C means that it has to be a ace of heart. So there is only one such card in the deck. So it is 1/52. And this is where you need to verify whether the product of these two is equal to this, and it is. All right, so we show that they are independent. Now, if you recall, we have when we introduced the concept of probability, we introduced a concept of about set theoretic concept. One of them is what we call mutually exclusive. Mutually exclusive means the events do not have common elements, do not have common outcomes. Okay. Now, if they are mutually exclusive, they can't be independent, because knowing one thing happens will exclude the possibility of the other things to happen, right? So, so the two things are two different things, and there is a little, a very minor error in the slides. I will change it. Okay, so here we wanted to clarify independent events and mutually exclusive events. We are talking about a pair of events for the time being. Later on, we will talk about more than two events at the same time. So two events, A and B, being independent and being mutually exclusive, I think this is a bit mild, are not the same thing, should we say are very different thing, all right? So A and B are independent if and only if, so this is a definition, if the probability of the joint happening is equal to the probability in the product of the individual probability of their happenings. I wanted to change the second line a little bit. So this is what I want to change. So A and B are mutually exclusive if and only if A intercept B equal to empty set. All right. So this is the meaning of this. But if they are empty set, so it will imply A intercept B would be 0. In a lot of situations, this is okay, but this is not always true. If the probability is 0, doesn't mean it has to be an empty set. All right. When we come to a continuous random variable, let's say normal distribution, for normal distribution to take exactly a point probability, it is equal to 0. So, but the set that the normal distribution equal to an exact number is not empty, but the probability is 0 there. All right, so these are some little subtle things. So I soon thought this statement very wrong, but I think a better one would be this. Okay, so A and B are mutually exclusive and non-trivial. Then A and B cannot be independent. Maybe sorry, I keep switching it back and forth. So the statement there means that probability of A positive, probability of B positive, and that A and B are mutually exclusive. Then what we have is that A intercept B, which is probability of empty set, and it has to be 0. And of course, this can't be equal to this, because this is positive, this is positive. All right. So that is the meaning here. Okay. I think a few slides down in this lecture notes, basically some of the examples is trying to model this. I'm considering two events, A and B. A and B independent. A and B are not independent or dependent. And then A and B, my handwriting is getting worse and worse, mutually exclusive. And then not mutually exclusive. I can be a doctor soon. All right. So, so basically, we are trying to look at examples where we have one of these four scenarios. But we have just seen that when A and B are mutually exclusive, these things can't happen. All right, because knowing A occurs will preclude the possibility of B to occur. So meaning that once you know something, once you know the information that A has occurred, you can be sure how to predict whether B will occur. So this situation is just what we have. And I think the subsequent few examples, I mean that you will see not independent but mutually exclusive, independent but mutually not mutually exclusive. I mean basically follow this table to examine all the possibilities. Okay, so the sample space S and the empty set are independent of any event. Okay, so there is a proof here. So I pick any event A. So the sample space, we handle one at a time. We look at the event which happens to be the entire sample space S. And so the conclusion here is if I consider the entire sample space as one event, and then if you give me any other arbitrary event, the sample space and the arbitrary event will always be independent. So this is what we are trying to do. So to verify that they are independent, basically I need to verify whether this is equal to the product of this. All right? So that is all I need to do. But then on the other hand, this is quite easy to do because this is equal to 1. So the very right-hand side is equal to the probability of A. And then the left-hand side, the very left-hand side, A intersect S, since A is an event, so A has to be a subset of the sample space S. So A is a subset of S, so A intersect S has to be A itself. So what it means is that the left-hand side and the right-hand side is both equal to the common value, probability of A. So therefore, they are independent. And also similarly, if you are looking at an empty set, so the joint happening, A intersect empty set will be empty set itself. So as a result, the probability of empty set would be equal to 0. But on your right-hand side, because the fact that probability of empty set is 0, 0 times anything will be 0. So your right-hand side will always be 0, and your left-hand side is always 0. So they would be equal. So that is why we have the conclusion in the previous slide. The sample space will be independent of any event, statement 1. Statement 2, the empty set will also be independent of any event in your probability considerations. Okay, if A and B is a subset, so that A and B are dependent except some, trivial cases, basically. And the trivial cases is that B is really huge. B is taking up almost the entire sample space. But this is not difficult. The calculation here is justifying it, but what is the intuition behind? Now, suppose you know you want to, the reasoning is, suppose you want to assess whether B occurs, all right? with the information, suppose you have an extra information that A also occur. Now, if A occurs, because A is a subset of B, B definitely has occurred. So meaning that your assessment of the probability of B would not be the same if you know A has already occurred. So, so that is it. Now, of course, the mathematical check would be this. I'm checking the left-hand side, probability of A intercept B. A intercept B because A is a subset of B. So A intercept B will be just A itself. So it would be equal to this. But then probability of the right-hand side is the product of these two individual probability. And it would be, now that is why, now you see why we have to exclude this case. Because if we do not exclude this case, there is a possibility that they are equal. And by imposing on this condition, the probability of B is not equal to 1, meaning that the probability B has to be strictly less than 1. So the product here is actually strictly less than probability of A. So the left-hand side is actually strictly less than the right-hand side. Now, check for independence. I think this is a good pointer here. The properties of independence, unlike the mutually exclusive property, cannot be shown on a Venn diagram. This means you can't trust your intuition. There is a little jump here. Basically, the word independence in probability has a very, very specific meaning, unlike the English understanding of the word independence. It helps, having our usual concept of independence, but it doesn't mean this is always the case. So these are the pitfalls that sometimes we do fall into it. So the only way, if you really want to check their independence, is really compute these three different probabilities and then show that the equation holds. All right? And I repeat it again, getting old, getting naggy. You don't calculate your left-hand side by multiplying the probability as in the right-hand side. Otherwise, you will always prove they are independent, which may not be independent. Okay, now, so this is the example 7, 8, and 9 is trying to do from what the table I'm trying to show you. So there is no point to look at mutually exclusive and independent case because our earlier discussion showed that if you have mutually exclusive, unless some trivial situations, the two events can't be independent. All right? So here, this is an example of mutually exclusive. So A is the event of odd numbers, and D is the event of even numbers. So A intersect D, because they are mutually exclusive, so it would be an empty set. So I think a little bit better, if you want to be extra clear, is to write one more equal sign, probability equal to probability of empty set and equal to 0. So, and then these two individual probabilities are equal to half, and actually all we need is all of them are positive. And so the product on my right-hand side will always be positive, but since they are mutually exclusive, the left-hand side has to be 0. Again, this is, but of course this is just mathematical check here, but if you keep the intuition in mind, it is almost clear. Because if I tell you I'm interested in predicting whether I will get an even number from a roll of dice, okay, by itself. But later on I tell you, oh, actually we get an odd number. So knowing that an odd number, then your hope of getting an even number will be dashed, okay? So they can't be independent. Consider throwing a dice. Okay. Now, the two events we are interested, the event of getting an odd numbers, and then the event of getting a small number. A small here means less than or equal to 3. So because of the device, the probability of each of the single events is equal to half. Okay, and now here that you have to do the this left-hand side by definition. So A-intercept B will be, you first look at this joint event. That would be only 1 or 3. And so as a result, the probability of A-intercept B is equal to 2 over 6. And that would be 1/3. And so 1/3 can be equal to a half times a half. So, and so A and B are not independent. So one more example, not mutually exclusive and independent events. So if you still remember the table, the 2-by-2 table that I just drawn, so there are 4 settings. One setting is impossible. There wouldn't be any example of having mutually exclusive and independent. And now these 3 examples illustrate each of the remaining 3 possibilities. So A is an event of an odd numbers, but now I enlarge it a little bit, 1 to 4. But you actually see what's coming, because this will be equal to a half, this will be equal to 2/3, and then A-intercept C will still be 1/3 as before. And now, because of the maneuver here, they both equal to 1/3, and so and the equality is okay. Now, so this is where the difficulty is. If you only have example 8, the tendency for you seems to suggest, without the calculation here, that the example 9, the 2 events will be dependent as well. I mean, based on your experience in example 8. But this example is cooked up in such a way that the numbers just match, all right? Okay. This is interesting. If A and B are independent, this is what we would expect, because basically saying that your assessment of the probability of B will not change at all, whether you know A has occurred or A has not occurred, right? So you are thinking of A. But saying that A has occurred or not occurred is the same as saying A has not occurred or A has occurred, right? I'm saying that A earlier is saying that A has occurred or not occurred, so I'm conditioning on the A itself. But if I'm conditioning on the A complement, it's just saying that A has not occurred or A has not occurred, so that is A occur, right? So I mean, so that is to be expected. The point is, of course, now I'm going to give you a proof, but I think the intuition is more important than a proof. A proof is really settle it, because our intuition may fail us, but it doesn't mean we shouldn't try to develop our intuitions. So the idea of proving, let's say, so I wanted to show A and B independent implies A and B complement are independent. Okay, so to prove this, I set out to check all right. So I wanted to prove this. Now, this is usually not recommended in high school, or I mean in proper mathematical presentation, but it is actually useful. You work on both sides until both sides meet, and then so the thing the thing on the top will be true. Okay. So when you read mathematics textbook or mathematics paper, people might have derived it in this way. I mean, the left-hand side I mean, at the same time, they try to simplify until they meet, and then they know it is true. But when they present it, they usually present it in a more streamlined way. I mean, either starting from one side and then go to the other side. All right. So, so I'm going to do the more intuitive way. So I'm working on one side at a time. What is the probability of B complement? This is we know this, right? And so we will have probability of A minus probability of A times probability of B, right? And this will be equal to probability of A. This is now, I use the fact that they are independent. Okay. And so what the picture is this. This is A. And the probability of A minus this. And so this would be the same as A intercept B complement, right? So actually, I get the left-hand side right away. So I don't need to move it here, all right? Okay. If you accept this, then we can deduce the others simply by iterating this. So A and B complement are independent. Now, iterating what we have, it means that we can, I think of this as my B now. So or another way to say it is just a little bit. If you are typing it, you can cut and paste. So B complement this. And so I can take the complement of the second one because earlier we take the complement of the second one. So I'm basically reiterating what I just proved. And so I have this. And of course now interchanging the role of A and B, A and B independent implies A complement and B are independent. All right. So that shows the theorem. But this theorem actually means our intuition actually carry quite a bit. If I have two events independent, so I can always keep the event itself or consider its counterpart, the A complement. And whatever you do, whether you keep A or the complement, the remaining transformation of the two events will still be independent. Okay, this is a bit morbid here. The probability that Tom will be alive in 20 years is 0.7, and the probability that Jack will be alive in 20 years is 0.9. Then what is the probability that neither of them will be alive in 20 years? All right. There is an area called actuarial where people, the company, takes in insurance according to some kind of a life table, predicting how long you will live, especially you buy life insurance. So they, they do this kind of things. Of course, not in this simple setting. Day in, day out. But also you can, you don't even need to think about it's real people, but you can think of it as some kind of a component. So, this is basically another way to see it is a risk analysis. You have a certain component, and suppose the machine or the system depends on two components, and the two components has to act independently, and so on. Now, there is a very big thing if you Google it. I think in 1986, I forget the name of the Challenger. The space shuttle, I think it's called a Challenger or whatever. I was a graduate student in U.S. at that time. I was walking on the street, and then there was the news that the space shuttle had an accident. And the investigation, that, actually, if you trace the story, one of the reasons is there are what they call the O-rings, the rings that hold certain things, and there are 6 of them. And supposedly, these 6 rings has to act independently, meaning that the probability of one get ruined will not. One component get ruined will not. The other components are functioning independently of the others. But somehow the design sort of pair them up, and so as a result, one is ruined, lead to a much higher probability of the other part that is ruined. So, and then that's it. And this kind of thinking is also very common in engineering, and actually you have been practicing it without knowing it. This is what we call increasing the reliability by having redundancy parts. So I think when you go for an important exam, you always bring your 2 calculators, more than one, right? Just in case one calculator spoil, which is very unlikely. You have been using it for years. I mean, why would it spoil on that day? But just in case, all right? You usually only use one ball pen, but you will bring a few. So basically, you are trying to minimize the probability by redundancy. Aircraft too, I mean, there are more than one system. Now, of course, there is another possibility of increasing the reliability, but that would require technological advancement. Suppose you have only one component with 80% reliable. That means 20% it will break down. By having a spare item exactly the same, if both of them fail, the probability is only 0.04%, not 20%. But if you were to make a system 96% reliable, that would be quite a big breakthrough in the technology. So it might be much easier for the time being to have a redundant part, just as a standby. Okay, so a lot of this kind of things actually happen. We have a spare, some other, I don't remember. I mean, like our elevators, we might have a spare part, that kick in the energy. If in case the outside there is an electric shutdown, so there is a spare battery that works. So we have been practicing it. So it is not just related to Tom and Jack, but it is actually just a particular example. So let A and B, actually this is the way the lecture is trying to solve it, but I would recommend you to use notation that is easier to remind you. So if I were you, I would like to use T and J. T stands for Tom and J for Jack. So it's easier to remember rather than you keep referring back. Now, of course, this is now, of course, I can understand it's not a problem for the young people. You have good memory. But, I mean, for old folks like me, I may not remember what is A. Then I have to keep referring back. And then my eyesight is getting worse. Then I have to, enlarge it. So anyway, so I would recommend you to name your events, not just ABC, but name it in a more suggestive manner. So at least it is easier for you to read, as well as if it's being presented to your supervisor or whatever, it's easier for him to keep track of. So let A and B be the events that Tom and Jack would be alive in 20 years. Note that these 2 events are independent. Now, there is a built-in assumption of independence. Suppose Tom and Jack are actually twins. They have similar genes. Then the independence would be a little bit stretched here. But here we are assuming Tom and Jack are not related. So hence A complement and B complement are independent. So this is where we use the theorem. All right. So this is guaranteed. This is no longer assumed. The assumption is earlier. Okay, we are assuming that whether he will be alive are independent. But as it turns out, whether they are dead, also independent. All right. So this is this probability. All right. Okay. Pairwise independent events. So now I'm considering n events at the same time. Now, one trick to learn mathematics is, I think many of us know it, is to reduce the problem to a smaller, a specific case. Now, we have spent quite some time on n equal to 2. I have 2 events. So maybe the next step to try to understand rather than this full generality is that n equal to 3. So, you just take time, but it drill in your understanding. Once you get it almost like your second nature, then it is very easy to generalize. So I have n events, and I introduce a new concept, pairwise independent. The definition is basically I pick any pair of the events from this list. The pair of events have to be independent. So this is the definition. Okay, mutually independent events. Now the definition here, if you look at some textbook, this definition here is extremely precise, very, very concise here. All right, because let me illustrate this with n equal to 3 or n equal to 4. You will see how this one-line definition actually replaces many things that you need to check. So let's look at A1, A2, A3. We wanted not independent. Now, if you only have a pair of events, then it is enough to talk about they are independent. But when we have more than 2 events, there are 2 concepts. One is that they are mutually independent, or people think of it as completely independent. Okay, and we will abbreviate it to independence, or pairwise independence. Pairwise would be A1, A2 are independent, A1, A3 are independent, and A2, A3 independent. So now I expand the meaning of the definition 13. So you have to check this. You have to check the particular pair A1, A2, and you have to check the particular pair A1, A3, and you have to check the particular pair A2, A3. And now, so this is a pair at a time, but here in the definition 13, my k now is equal to, so this is the definition, k is equal to 2, and then k is equal to 3. So I pick 3 sets, 3 events at a time. So I have A1, A2, A3, and it is equal to their product. Okay, this is only for n equal to 3 and n equal to 4. You will have the probability of A1, A2 equal. I'm not going to write this. You can fill it in. A1, A3, A1, A4, A2, A3, until A3, A4. So you should have 6 of them. That corresponds to 4 choose 2. Okay, this is k equal to 2. And then k equal to 3. There are 4 of them. A1, A2, A3. Okay, and the last one is A2, A3, A4. And this is that is not it. You still have k equal to 4. So now you only have one such situation. Okay. So what it says is that all your right hand sides here will be the the product of the individual probability corresponding to your choice here. All right. So basically, when you have independence, you can build up the probability of the joint happening by the individual atoms. The individual atoms are the individual probabilities. So that is where the independence is. And there are altogether, I think there is a formula at the back. So it's 2 to the power n minus 1 number of equations you need to check. So for n equal to 4 here, is 2 to the power 4 minus. So 2 to the power 4 is 16. So you have to check 11 such equations. And then here you have to check 4 of them. So this is exactly what I was trying to say. This definition is very innocent, but it is highly condensed, all right? So basically, the definition is trying to say, first, you pick any number of events in your consideration. So you can pick 2 events or 3 events and so on. And then if you decide to consider all the 2 events, then you have to exhaust all the possible pairwise. If you decide to have 3, you have to pick all the possible 3 from the list. So that is what we need to do. Okay, maybe I'll have a little break. Maybe I'll finish let me see. If I keep finishing it, then you won't have a break. So maybe we'll stop here for a while. And so let's come back, say, at 10:52. Okay, let's continue. I mean, I have to be honest. Of course, I can show that this is independent, but then when the sum is 6, then it is not independent. Some other questions that have been raised is whether the first die equal to 4 or 5. You will see in terms of the working, a lot of things can be carried over. So the only possible change would be depending on your sum. So here 6 has to be 5, and if the sum is 5, it will be 4, and so on. So you have to make change here. And then of course, in most of the cases, it would be one outcome. But there are also situations that I mentioned. If I tell you this, the first die is a very big number, let's say 6 or 5, then I mean, you just know that the sum can be very small anyway. So, so it would be either 0 outcome or 1 outcome. So as a result, this is either 0 or 1 over 6, either 0 or 1 over 36. So you can actually work it out. But I mean, the thing is, how do I intuitively convince myself 7 is so special, and then the other numbers? I mean, I confess that I can't have a very good explanations. Okay, so if you have some more intuitive explanation, let me know. So we were talking about this. Okay, another question that was raised about Tom and Jack. The question itself should have been a bit more careful that Tom and Jack are unrelated genetically. So of course, this is difficult to, I mean, again, all of this kind of description is very difficult to make precise. If I say they are genetically independent, does it mean that, I mean, they have to be a different race, right? And if you push it far enough, everyone, I mean, are descendants of Mother Eve, right? So, there are certain reasonable. But of course, one of the most reasonable thing is I won't think that Tom and Jack are, I mean, related within the family. I know of a family, the family, I mean, suffer cancer, and I mean, the parents died quite young due to cancer, and then the family of 4 children, I think 2 of them have already died due to cancer. So there is genetic, the heritage there. So I mean, here is just making the assumption. So of course, you are right. I mean, the assumptions are not spelled here. So one of the things that you learn in an academic setting is actually you are aware of what you are assuming in, and then even though when the description of the story doesn't say this, because people on the street or people in another discipline use another set of language. So I mean, it takes some time to communicate. I basically trained in mathematics, but about 19 years ago, I started to do bioinformatics and computational biology. So I have some experience interacting with biologists, and it really takes some effort to I mean, to understand each other. We are speaking different languages. Not only just languages, but also the culture of seeing things, right or wrong. For example, in biology, they have a saying that every principle will have an exception. Now, to us, I mean, then it is not a principle, right? So, but anyway, so we are living in a pluralistic world. So different people. Okay, let me emphasize this again. This is a very innocent-looking, very, very condensed statement. What later on it says that if you want to verify, I think I saw it somewhere. They describe how many such equations you have to check, right? Oh yeah, here. So the thing that is described. So this is just describing. In detail. So you have to do it pair by pair. So you have to exhaust all the pair. And then later you have to exhaust all the 3 at a time. And then later 4 at a time and so on until everyone together. And there are altogether 2 to the power n minus 1 equations that you have to verify. It would be your good fortune if you come to one equation that does not hold quite early. Then you don't need to do the rest, all right? So the requirement is that it has to hold for all of them. If one of them fails, then we will not say that they are mutually independent, all right? So again, this is a very, very specific, very narrow kind of a definition, okay? Mutually independence implies pairwise independence, okay? Because pairwise independence, you have to check 2 at a time. So in the process of checking it, you have already done 2 at a time. So, but the converse of the statement is not true. Okay, so if you have pairwise independence, it does not mean they are mutually independent. Now we will come, I think there is an example illustrating, or what we call a counterexample. A counterexample that we cook up a number of events and they are pairwise independent, but altogether they are not independent in our definition. But the first thing is the intuition of theorem 10 carry over, meaning that if you are having a list of A1, A2 up to AN, then it is up to you whether you want to take the complement of each, some of them or not some of them. So it's really arbitrary. Suppose you have a list of n events and you know that they're independent. Then for the first event, it is up to you whether you want to consider the event itself or the complement of the event, and so on. So it's up to you how to modify it. So you will come up with a list of n events. The list is modified by individually whether you decide to take complement or itself. And so it will still be independent. So that is the remark here. Okay, so if we know that A1 up to AN are mutually independent events, whether you take the event as itself or you change it to its complement, then the new list, B1 up to Bn, will still be mutually independent. So whatever you do to the individual event, here the operation is complement or not complement, will not affect the independence. So it is being inherited in that sense. Okay. Okay, now I look ahead first. So here is an example of mutually independent for 3 events. And then now this is an example, a counterexample for a pairwise independent but not mutually independent. So this is an example to substantiate this statement, the but here. All right. So let's look at the examples. So I have a fair die and I roll it 3 times. The probability that the first toss gives an odd number, the second toss gives an even number, and the third gives a value greater than 4. Now the fact that actually each individual event relate to separate action, all right? So, so it is highly likely that they will be independent because whatever you do in the first event and then will be independent of your second toss. Now, of course, Here we assume the toss is being tossed rigorously. I've told you, I don't know whether I've told you, a lot of randomness could have happened is because we are amateur and we are not doing things in a very controlled manner. I've mentioned to you flipping a coin. The fact that it is half and half is because we flip it rigorously and then we are not trained. I've seen people who are trained, they can control what they will get, either head or tail, with a reasonable accuracy. It is basically a matter of physics, where you hit the coin and how hard you hit the coin, because where you hit the coin determines the rotation, and how hard you hit the coin, it depends on the time. And there might be people who fake it, meaning that faking their action, that they are actually, flipping many times, but actually only a few times, but even though it's in the air, all right? So the motion is actually mostly just stay in the air, but it does not flip that many times. Again, another thing is you remember the dovetail shuffle of the cards. So you break a 52 cards into two piles. One, you hold one pile on your left hand and another pile hold on your right hand, and then you randomly drop it. Now for amateur, for us who are not trained, when we break it into two piles, the two piles are of different sizes. If you are really good, you always divide into 26, 26. Now, suppose that my right-hand pile is the lower part that I separate. So I have the first top 26 cards, and then the lower 27 to 52 cards. So if I drop my 52 card first, and then I drop my last card on my left hand, which is 26. So the new deck later on will be 26 is my second last card, and 52 is my last card, right? So if I really do it interlaced, this is what we call a perfect shuffle. I might have mentioned to you, you can actually try it. You just systematically write it down. After exactly 8 shuffles, you get back the same arrangement as your first. So there is no randomness, all right? And so randomness come in is because we are not good. So we divide sometimes 28 on one side, 24 on the other side, or sometimes we might have 30. And then when we drop, we are not interweaving it. We are dropping a few cards here, and then sometimes one card here. So this turns out to make things random. All right. So here we assume it's being tossed quite rigorously. That means you are actually not purposefully trying to get certain things. But this is not the case, especially when you're playing Monopoly or some other board game. You always want to have a certain number. Then you try to, at least you try your best to control your hand a bit, and so on. Now, at this point of time, I want to digress a little bit. In casino, I think you more or less know that already, but just to remind you, in the slot machine, sometimes people think that they can control by pulling harder or, control it. No, it is controlled by a software. So whether you push real hard or, it would be the same, randomness from the software. It's just like when you are waiting for the elevator, you press the button harder, will it come to you faster? It won't, right? If you press it 2 times, it still takes its own sweet time to come, all right? The same thing is I just learned in this claw machine where you move a claw and then get your favorite teddy bear. Again, you think that you can control the movement and the grip strength. I was told it is actually a software behind. So you think that you're clipping it very tight? No, the software is controlling your strength. And then they also design such that once in a while you get your teddy bear. Because if you don't get your teddy bear after many tries, you won't try at all, and they will lose a customer. So a lot of these things are not, what you think. All right, so here we imagine we are rolling the die in a mechanical way, a normal human, not trained. Okay, so A is the odd number in the first row, B is the even number in the second row, and C is the 5 or 6 in the third row. So we just do the calculations. Now, let me explain the denominator. The others will be very similar. So the denominator is I roll the die 3 times. So each time, each row, I have 6 possibilities. So I have 6 times 6 times 6. So this is the denominator. And now A concerns about whether I get an odd number. Is it an odd number, right? Odd number for my first row, and then I don't have any constraint on my second and the third row. So I only have 3 such outcomes for my first row. And then since I have no other constraints, so it would be 6 times 6. So it will work out to be 1/2, 1/2. And then this will be 1/3 here. So as a result, you can check. Now, this side, you have to work it out again. A-intercept B. What is A-intercept B? A-intercept B is you get an odd in the first time and then an even. So here, the 3 is referring to the 3 odds that you can have in your first row. And then this is the 3 even number that you can get in your second row. And you have no constraint on the third row, so you have 6. So as a result, it is 1/4. And 1/4 matches the product of these 2 half-half. So it is this. You follow the same method, but except that you have to be careful about the numerator in all of them. And so it worked out to be equal. So up to this point, we have verified that they are pairwise independent. All right. So one last equation to check, and that is this. So I want an odd, I want an even, and then what is C? And then I want a 5 or 6 in my third. So I only have this, 3, 3, 2. So as a result, this is 1/12. And so it is turned out to be equal to all the product of this. So they are mutually independent. So I've verified all the possibilities. So it is really a pain, all right? I agree that to check they are mutually independent. Very often this is very difficult to check, honestly. But it is very useful to use if you know they are mutually independent. And that is where why there are some abuse of misapplication of this. Because once you know that they are mutually independent, computing the left-hand side, especially these are the composite events, joint events, and you can reduce it to individual events to do the calculation. So that is where the convenience of the independence. So the question is whether it is applied in the right way or in the wrong way. Okay, I roll a pair of fair dice, and the first die shows an even number, and the second die shows an odd number. So from our previous result, if I only look at A and B are independent, and the 2 dice shows both odd or even numbers. Now, definitely, I mean, can be true, right? In some way later on. Okay, so we go through the same calculations, so as before. So we will up to here. I won't go through the detail; it will bore you to death. But the upshot is that they are pairwise independent. So this is the thing. And now, if I have A intercept B intercept C, this is impossible because A is about odd numbers in the first row, and then B is about even number in the second row. C is they are either both odd or both even. It can't happen, all right? Given that you already have an odd in the first place, even in the second place, then they can't be both odd or both even. So, so I will have no outcome here. So as a result, this is 0. I basically don't need to check because these are all positive numbers, okay? And so they are pairwise independent, but not mutually independent. So you really have to check everything for mutually independent. Now, the probability that a grader will make a marking error on any particular questions of a multiple choice question exam is 5%. If there are 10 questions and questions are marked independently, what is the probability that no errors are made? And that at least one error is made. We will see this again later on, and this will be something related to binomial distribution. All right? You are repeating something in an independent and identical manner. And then each time you will have a certain probability of success. In this case, the success probability is marking it wrongly. It's 5% here. So we are doing it in a very specific manner, but we can reason it out. So suppose EI is the event of making an error in marking the ith questions, then E1 up to E10 are independent. All right. This is the assumption built into the questions. And then E1 complement up to E10 complement are also independent. This is a result from our earlier discussion. The required probability is now is the complement of all of them, so meaning that there are no error made. So this will be 95%, and so I have 95% to the power 10. I think this number is not pretty. It's about 60 something. So having a faultless marking of the 10 multiple choice questions is only 60% of the time. All right. Definitely NUS is much better. All right. The required probability is given is at least one error is the complement. Now, why is this is again advertisement here? If you are calculating this probability directly, that can be difficult, because what it means is that at least one error. So you should break it down into exactly one error, exactly two errors, exactly three errors, and so on. But the opposite of this is only one such scenario with no error, and so which is easier to calculate. You don't need to consider many cases. So it would be 1 minus 0.95 to the power 10, which is here. So this is it. So for the last questions, we can replace 10 by n, basically. Why? Because, in fact, if I have n questions, my subscript here, the 10 will be replaced by n, and then this will be replaced by n. So basically, I have n terms. So I have 1 minus p times itself n times. So it would be 1 minus p to the power n. All right, and the part B will be just 1 minus the opposite probability. Okay. This is the one of the most important thing, especially nowadays. The Bayes theorem make a comeback. A lot of simulations and all this, a lot of scientific reasoning is to incorporate. For example, you want to say, for example, Tom would live beyond 20 years with a certain probability. Now, there are some ways to do it. You look at all those people around his age, and then and look at the past data and do some estimations. So this can give you a pretty good clue. But on the other hand, if you, as I mentioned, if you look too far way back, then whether the historical data has changed. For example, if you're looking at life expectancy, before the penicillin is discovered, any infection is very lethal. So if you look too far back in history, because of the changes of technology and the time, then your estimation may not be the same situation that you are dealing with. So frequency approach gives some answer, and certainly sometimes it's not. And sometimes, for example, you want to see whether the market will crash because of the, a lot of things happening between U.S. and China, Brexit, and other things. Now, different people will come up with different, view of the market. And so some people wanted to say, oh, maybe we should incorporate not just a hard parameter, but the parameter is coming from the opinion of many experts. Okay, and how do I build it? And so this is, why the Bayes theorem is making a comeback here. Okay, we are not going to describe this in its full, but this is the thing here. The first thing is this picture illustrates what do I mean by partition. B1 up to Bn are mutually exclusive, and then Bi. So what it means mutually exclusive, we have seen it before. I mean, meaning that the B's do not have any common elements. All right. So if you look at it, the Venn diagram, they do not have overlap. All right, basically. Now another term, exhaustive. Exhaustive means that if you group them all together, it would give you the entire sample space. All right, so this is it. So you basically exhaustively enumerate the possibilities, and that is what is going on. And then your enumerations do not have overlap. All right, so case 1 and case 2 do not have some common situations. So that is the mutually exclusive requirement. And now I have a particular set A that I'm interested. So I wanted to compute the probability. So there are two formulas. This is called rule of total probability, or some people refer it as the Bayes formula 1. Now, so actually we are deriving it. The usual formula will be just the left-hand side probability of A and equal to the last equality here. Okay. The top part is basically a proof. So and when you check the textbook, usually they would give you probability of A equal to this without going through this. All right. So let me just fill in a little detail of the proof here. I mean, actually, the first line here almost gives you everything, except a little detail. Okay. So the first thing is, probability of A will be equal to the probability of A intersect S, right? Because A is a subset of the entire sample space. The red color does not come out well. Is it because my focus is not good? Okay, I think it's a bit better. So here we make use of the fact that the B's are mutually exclusive, are exhaustive, because the union gives us back the S. And we use the distributive law to consider this. All right. But now the fact that the BI and BJ do not overlap, and A is somewhat here. So A intersect BI and A intersect BJ, of course, have to be mutually exclusive too. So let me state it. A intersect B1, this event, A intersect B2, ... A intersect Bn, they are also mutually exclusive. So as a result, we can have the sum here. Okay, so this is the part that I'm connecting it with the in your slide, theorem 2. Okay, is that all right? So once you have this, then we can so this is my okay. The notation is without the intersection sign, so this will be this, and so here I have this, and this is just the multiplication rule. Now so this is just a formula, but the way to understand it is that I think of the B1, B2 up to Bn are the possible causes of certain experiment. One example is we will visit this problem, whether a certain person has cancer, and then the person may not have a cancer. So these are the two different causes. And then this person undergoes a certain diagnostic test for the cancer. So the result might be positive or negative, and so on. So what we are interested in is how many positive cases that are reported by the test. So, so the positive part is the A here that I wanted to look at. Okay. So there is another way of seeing this. The rule of probability is closer to a lot of people think of it as a decision tree or probability tree. So you think of these are the causes. So it could be the cause we call it B1 or Bn. Okay, so imagine you have a subject, and so it goes into one of these cause. And so I have this. And now for each of the cause, I have an effect. We call it A. Of course, I don't care about the others. Let's say non-A. All right? And so I will have this A, and then I will also have non-A, and so on. Okay, so here we have the probability of B1. How likely the cause due to B1 occurs, and this will be probability of B2. And this is probability of Bn. And so, of course, this will be the conditional probability. Knowing that the cause is due to B1, I wanted to calculate the effect. So this is usually known, all right? So I have this. So as a result, coming from this branch will be probability of A condition on B1 times the probability of B1. And of course, but this is not the only contribution to observe the effect A. So it can come from here. And so on and so forth. Okay, so you just have to add them all up, then to give you the probability of A. Because in order for A to occur, you have to go through one of these possibilities. And so once you fix a possibility, then you follow this branch. And so that is why it's called the rule of total probability. All right. So because you basically go through all the possible causes, and then you total them up, all right, due to different causes. So it is a matter of things whether you are more comfortable with some visualization like a tree, or manipulating the formulas. So different people have different preference. So this is rule of total probability of the Bayes theorem 1. So this is the assembly plant. We have a similar questions in tutorial 2 about the drain. The drain can be filled in by machine 1 or by machine 2 and so on, and whether the bottle being filled is conforming or not conforming. So it's the same thing. So in a certain assembly plant, 3 machines, B1, B2, B3, makes these mistakes, all right? It is known from past experience, 2% of the machine B1 will make this kind of mistakes. So now, suppose the finished product is randomly selected. What is the probability that it is defective? So basically, I know the machine B1 will make 2% mistake, but it also depends on how the overall proportion of things that are made by machine B1, right? So altogether, so B1 will contribute 2% times 30%. All right. What does this 2% mean? All right. So let me see whether they define it. Okay, so maybe I think I follow the decision tree, it's easier. So it says that the machine B1 will manufacture 30% of the product. So I have this branch upon 3. And then 45% is going through, is produced by machine B2. And then this will be 25%. So this is actually the distributions, how likely a certain product is made by various machines. And then different machines will have a different capacity of making error. So that would be 2% here, and that would be 3% in here. So if we follow this route, so it would be 0.3 times 0.002. So you work it out, and so on and so forth. All right. So as a result, this is the total. The percentage of making a mistake from one of the 3 machines is 2.45%. So basically, it's somewhat like an average of the 2%, 3%, and 2%. But this is what we call a weighted average. It's weighted because different machines make different proportion of the product. I mean, some machines make a little bit more, and some machines make a little bit less. So this is a weighted average. All right, weighted according to what is the percentage of time that the machine is contributing to the product. Okay, voters. In a certain county, 60% are Republicans, 30% are Democrats, and 10% are independents. When these voters were asked about increasing military spending, 40% of Republicans oppose it, 65% Democrats oppose it, and 55% of independents oppose it. So what is the probability that a randomly selected voter in this country, and so on and so forth? Now, you notice that the Republicans has, less likely to oppose the military spending, increasing the military spending. But at the same time, in this county, there are more Republicans, so they should be weighted a bit more, all right, in terms of this. So these are something that we always do, but we just formulate it in terms of the base formula. So if you think about it, okay, this is nice. So I let O to denote opposing the increased military spending. But of course, we try to avoid O, especially when we are writing it. Sometimes you can't tell whether it's an O or a 0. In my case, sometimes people might think there's a D. All right. So anyway. But this is nice because R stands for Republican, D for Democrats, and I for Independent. So it's very explanatory, self-explanatory. So we do this basically follow each branch, and so it's almost like it's exactly 49%. So it's almost like 50-50%. So if you pick randomly from one, it's either yes or no, with almost close to 50%. I don't like fish, and and it's quite similar. So let's skip it. All right. But later on we will revisit this. We are tracing the blame. All right. Now the chef and the assistant are different in the skill. Now, this is the situation. I now know the fish is burnt, so is it more likely from the chef or is it more likely from the assistant? And then I wanted to be a bit more precise about the probability. Of course, it's more likely from the assistant, all right, but how much? So we can quantify this. Okay, and drawing balls. We have 4 black balls and 3 white balls. I think we can skip this, right? Okay. I want to end this with a little thing because I've been dying to show you. Monty Hall, this is a remake of the famous TV series not a series, but a game show. This is the earlier one. I think it runs over 10 plus years. But actually, if you think about it, it's quite lame. I mean, except that if you, I think a lot of these games, because of the price, the Wheel of Fortune, I remember when I was a graduate student in the US, I already watched it, and it's the same guy. And now you can still watch it in Channel 5. So, and he's the same guy, all right? He does not age that fast anyway. So let's make a deal run for a long time. And Monty Hall is the name of this guy. He's the game host, all right? And so there are a number of simulations. I think there was a time, New York Times, if you go to their site, then you will have this. Now the game actually is, there are 3 doors. Monty Hall is the host. And so one of the contestants is picked. Behind one door is a car, a big prize. And then behind the other 2 doors, I was told, are goats. I always wonder why, how do they keep the goats quiet, all right? But that is besides the point. Probably they sedate the goat. So suppose you are the contestant and you choose one of the door. Okay, I choose this. Okay, I'm the contestant. And now the host will, so there are 2 doors that are not chosen by you. So the Monty Hall will open one door and reveal a goat. So now he is very generous. He asks whether you want to switch, meaning that you want to change your mind. So by changing your mind means that you choose this door. But if you don't want to change your mind, you will stay. So, I mean, this is the skill of the Monty Hall. I mean, he keeps everyone excited. And then you heard voices that, stay, stay, stay. And then switch, switch, switch. Okay. And now some people argue it this way. Equally likely. Oh, I took the class from you. So there are 2 doors. Behind one door is a car. Behind the other door is a goat. So it's half and half. So the argument is if I stay, it is half. If I switch, it is also half. Why bother? So stay, right? Equally likely. My prof told me. So now, and then there are people. So actually, if you read about it, there was a lot of controversy. There was a lady, known to be one of the smartest women on earth, at her era. So I think she wrote a column I'm not sure whether it's a tabloid. But anyway, she solved the problem. She explained exactly how one should switch. And then simply because she's a woman, and a lot of people attack her. And also even some math professors attack her. So that makes the whole thing even more controversial. And people interview Monty Hall. What do you do? I mean, do you really open the door in a random way, or you actually know where the goats are? Now, of course, Monty Hall want to keep his job, right? So he wouldn't tell you. So basically, it's this. What do you think? We'll end here, okay? I'm not giving you the answer. You probably might read the answer later on. What is your gut feeling? Should you switch or should you not switch? Okay, I have only 2 stay, and then so the others all won't stay, right? I mean, only 2 of you say switch, so the rest will say don't switch, right? Okay, I'll let you play, so I'll end here. All right. Now another side question is, why did the TV station use 3 doors, 1 car, and 2 goats? Would it be more fun to have 4 doors, 3 goats, and 1 car? And Monty Hall will open 2 doors, so the scenario is still 2 closed doors. One is your choice, and one is your option to choose. Think of it this way. If you find that for 3 doors, the argument is a little bit elusive to you, push it to extreme. So this is another way of thinking. Either reduce a problem to a simpler setting. so that you can understand it, or push it to an extreme situation. Suppose you have 100 doors and only one car, and then 99 goals. You have it has to be held in a stadium. And then, so once you pick a choice, Monty Hall opened 98 doors. Still having 2 doors, one is closed, one is open. Now, if you are able to feel the intuition about 100 doors in this case, that would substantiate your thinking for only 3 doors, all right? Okay, I'll stop here. And if you want to play with it, I think there are some online, and then they let you play how many times. So you can play 1,000 times, all right? And then they will keep track of whether you change your choice or you keep your choice. So this is basically now a frequency approach. You play the game over and over again and estimate the probability. But we'll be able to calculate the probability anyway. So let me stop here. So you can spend your weekend on Monty Hall.
A few ago, you went through this Hall pageant question. Right?
Yes, yes.
So for B,